Well, at the start of this problem, I want to remind you that every one of the laws that we've looked at generally can be broken down into parts. And so I've actually started setting up what I thought would be like cheat sheets for each law, how to dissect it and where to start. For EMF, that cheat sheet would start with knowing that there's two parts to dealing with EMF. This is the final step, not the initial step. The initial step is to note that this requires you know the flux first. So the first step in any of these is to identify the area, identify the magnetic field, and identify the angle between them. And that's before you can even do the summation. So looking at what I have here, the bar is moving to the right, so I'm just going to label this distance x because I don't have a placeholder distance here. I know that's changing. I know the x is going to be the thing that's important, but I need a way to calculate the area. So I see that there's an area here. This region is the area that is currently being exposed to the magnetic field. So all flux begins with finding the area that's going to be exposed to a magnetic field, and to ask yourself, how is that area aligned with the direction of the magnetic field? So hopefully you recognize that just from looking at this, I can write my integral as, well, I'm not even sure how to write it as an integral. I think I just write the result as b times x times d times the cosine of 0 degrees. I don't need to integrate. I would only have to integrate if the magnetic field, the area, or the angle were somehow changing relative to the other. So, for example, our issue yesterday, where the magnetic field was not uniform in the region of space, that's where I'd have to integrate. Or if the angle were changing in the region of space, I'd have to integrate. But for the most part, you shouldn't have to ever integrate the flux. Your issue is to build a flux knowing that one of the variables is likely to have to be invented by you temporarily to get you to a point where you can find the derivative. X is a variable invented by me that wouldn't be given to you in the problem as a means for you to work the problem. I need an area. Once you have found your area, you take the derivative and you look for which one of these variables is changing. You know that going into the problem that you're going to be putting together something about the flux where one of those variables has to change. X is the one that's changing. It's changing with respect to time. So my next step is to go ahead and employ Faraday's law by substituting in for the flux, knowing that most of these are hopefully going to be constant and one of them is changing. So I know my n is 1. I know the negative sign is going to be about direction. We'll handle that in a minute. And that produces an EMF that is B times D times V. We did this problem already once. I'm just bringing it back. Now, I'm going to stop for a minute, and I want you not to use the right-hand rule. I want you to use Lenz's law and tell me what direction the current must be going through this bar. So if I see any of these, I know you're not doing what I asked. Use Lenz's law. What? If you take me off subject, I'm going to be frustrated. Oh, and I'm glad you found the answer. And I promise a time for you to tell us. So Owen, do you know the direction of the current here? Five, 4, 3, 2, 1. There's So either point up or point down. What is the direction of the current through that bar? So if science was ruled by majority, then we would say down, because that's what all of you said. The flux out of the loop is increasing. That has to generate a current that will produce a magnetic field into the loop to try and oppose the change. So that would have to be a current that is downwards. Good job. Now, you understand, if there's a current passing through this wire, and by the way, what's an expression for that current passing through that bar right now? Do you even know where to begin? Yeah, that's where I would begin. Ohm's law. So I think we can write the current as the voltage over the resistance. That would be the current passing through the bar at this moment. We have a current passing through a wire in a region of space with a magnetic field. That means there must be a force on this bar. A force on the bar from the magnetic field. What direction would that force have to be? This one you're going to need your right-hand rule for. I'll just to remind you, F equals IL cross B. This is what we're doing here. In fact, in the case of this problem, it'd probably be ID cross B, since D is the length of the wire. D, but the current is downwards, magnetic field out of the board. The force is to the left. So right now, there is a force on the bar to the left. There has to be. Think it through for just a minute. Physics doesn't give you something for nothing. If there was no force here, this bar could just slide across the rails, producing electricity forever. You don't get something for nothing. If you want to produce electricity, you're going to have to pull with a force that is at least equal to this force in order for the bar to move at a constant velocity. Please take a moment. Tell me the size of that force. What is the size of the force I would have to apply in this direction in order to move the bar at a constant speed? It's all right in front of you. You just got to combine two things together. All right, so don't want to spend a whole lot of time here. This cross product is sine of 90 because the bar's current is perpendicular to the magnetic field. So all I have to do is sub in the current, and I'll find that that force that's acting against the motion of the bar is equal to, let's see, B squared D squared V over R. So you must pull with an equal size force in order to get that bar to move across those wires at a constant speed. Let's say you pull that bar a distance L across the wires. Okay? I pull at a distance L. The amount of work I would do would be equal to F times L. It's constant force, right? That'd be how much energy I would require of myself to get the bar to move across the rails. In fact, we can write that down right now, that the amount of energy I lose to pull that bar would be B squared, D squared, V times L all over R. Now, you probably don't know where I'm going with this, and that's okay. I just want you to see something. Everybody get that written down, because I'm going to slide it off the screen. Infinite whiteboard, but still got limits. While that bar is being pulled to the right, there is power dissipated at the resistor. The power dissipated at the resistor is going to be I squared times R, right? So the power dissipated will be B squared, D squared, V squared over R. I'm just using I squared R. No big deal. Now this is the rate at which power is being consumed by the resistor. Are we following so far? We doing okay? I'm seeing some confused faces, but I don't have my glasses on. It could just be indigestion. But us pulling on that bar is generating power. And the power being consumed by the resistor is this amount. If I want to know how much energy is used by the resistor, it would just be equal to the power times the time it takes for us to push that bar across the rails. It's moving at a constant velocity, though. So if I say distance equals velocity times time, wouldn't that be L equals velocity times time? And couldn't I just solve this for t and say that the time it would take for the bar to travel across the rails would be equal to the length of the rails divided by the velocity of the bar? You may not see where I'm going, but I guess we can lose the picture. I'm just going to substitute all this crap together and just look at the energy consumed by the resistor as the power, B squared, D squared, V squared all over R, times T, which is going to be L divided by V. And I'll find that the energy consumed by the resistor is equal to B squared, D squared, L, V over R. How much work did I do? You see the work I did, right? This is the amount of work I did physically pulling the bar across the rails. This is the energy dissipated by the resistor due to the electrical current produced by me pulling the bar across the rails. You get that they're equivalent, right? The point of this is to say that this is a one-for-one exchange. Every joule of energy I put into this becomes 1 joule of electrical energy in my circuit. Except I'm probably forgetting something. That doesn't seem like how the universe works. I like this one-for-one exchange because that would suggest that we just convert any energy into any other source. But we have to operate this power plant in the real world, right? And in the real world, there would probably be friction here and air resistance. I mean, all of those things don't go away just because we have this perfect physics problem. I bet I would have to pull with more force and do more work myself than the actual real energy I get out. But one, I think, important implication is that aside from the amount of energy I will lose to frictional forces, the energy you put into the system is directly attributed to the electrical energy produced. As you close up, that I need to finish, but I want you to think of this for just a minute. What if I see if I can do this. What if I let gravity do that work? I set up a set of rails, and I let the bar just fall down the rails. You understand that as gravity pulls it down, it's going to accelerate the bar. But as the bar accelerates, the force from the magnetic field will increase. This is going to have a terminal velocity determined by the magnetic field, not air resistance. This is how magnetic braking systems work, stuff like that.